Good day. Another day, another chance to learn. So today we are going to look at writing an expression for the equilibrium constant, which is our Kc. Okay. So number one there, we're going to say for the reaction, we are given a hypothetical reaction there of 2A, which is a gas, plus 3B, which is also a gas, to give us 3C gas plus 2D gas. Okay. So in this case here, we're asked to write the Kc expression. If you're asked to write the Kc expression, you're going to say the concentration of products over the concentration of our reactants. So in this case here, I'm going to say concentration of my products. My products are C and D. So in this case, I'm going to say C, then multiplied by or add the exponent of 3 there, then multiplied by the concentration of D, and then power of 2, like that, all over then the concentration of my reactants, which is A. So concentration of A, then exponent 2 there multiplied by the concentration of what? B, exponent what? 3, like that. Okay. So these are the exponents there, the two from the ratios there. Okay. So number two, it says only gases G and solutions appear in the Kc expression. So whenever you encounter a solid or a pure liquid, right, you should not include this in your Kc expression. Then number three reads, the equilibrium constants does not have units. There are no units for Kc. So after writing all this Kc is not going to have what? Any units. There are no units here for Kc. Then number four there, the larger the Kc values are, okay, reactions in which the concentration of products is high in comparison to that of products. Such a reaction proceeds well to form a product. So in this case, we are going to have more of what? Of products. Why is that so? It is so because remember, we're dividing the concentration of what of the products by the concentration of the what? Of the reactants. So at the end of the day, if we're having a larger Kc value, it means here for our products here we're having a bigger number, and then we're dividing it by a smaller number there. Then a small Kc value, it means here reactions in which the concentration of the products are actually low, in comparison to that of the reactant. So in this case, it means we are dividing a small number by a bigger number. Then number six, it says only temperature can change the Kc value. Okay, so only temperature can change the Kc value. Take note especially of this when it comes to multiple choice questions. They are going to give you concentration, pressure, temperature, maybe as well as a catalyst. But you have to know only temperature can change the Kc value. Therefore, the Kc value for a reaction is given at a specific temperature. Okay, then here we're going to say Kc is not a Kc expression. So in this case here, we're saying if you were to write your Kc expression in terms of like concentration of products, like that, over the concentration of the reactants. So in this case here, we are not going to get any mark. So whenever you're asked to write down the Kc expression, or you are working out the Kc expression, if you start with this by writing concentration of products over concentration of reactants, you already forfeit the mark for the formula there. So this Kc concentration of products over concentration of reactants, if you write it like this, you forfeit the marks. So this is not a Kc expression. Then we're going to proceed and look at the rise table there. Okay, so here we're given a question. It says a certain amount of nitrogen dioxide gas, which is our NO2 there, is sealed in a syringe at 25 degrees Celsius, right? So you can see now we're given a specific temperature there. And then again, this is a closed environment. So you can see there it actually says what? Sealed. So when the equilibrium is reached, the volume occupied by the reaction mixture in the gas range is 80 cubic centimeters there. That's our 80 cubic centimeters. Then the balance chemical equation for the reaction taking place is, so we are given a balanced reaction there, which is our 2NO2 gas to give us a product of N2O4. So these are our products. And then on this other end here, we're having our reactants. Okay, so I can, as you can see also that our delta H is less than 0. Delta H is less than 0, so this is an exothermic type of a reaction. So question number 1, the 1.1 reads, define the term chemical equilibrium. So chemical equilibrium is defined as a dynamic equilibrium, okay, when the rate of the forward, when the rate of the forward reaction equals the rate of reverse reaction. Okay, so this is what we are having there as a definition for chemical equilibrium. Okay, so then we proceed to the next question that is actually going to be based on the Rice table, right? So now we're saying is a continuation at equilibrium. At equilibrium, the concentration of NO2 gas is 0.2 mole per dm cube there, right? We're given the concentration of what? NO2. Then the equilibrium constant for the reaction is 171. It's a temperature of 25 degrees. Then we have been asked to calculate the initial number of moles. So initial number of moles and of NO2 gas placed in the gas syringe like that, okay? So now if we are to go up there at the top there, we know we're given a volume of 80 cubic centimeters, right? Okay. So now to just like break down this rice table, what we are having here. So we're going to say here we put our R, which is our rice for our rice. Then the R represents our ratio. Then after the ratio, the I represents our initial moles. Then the C is the change in moles. Then E is our equilibrium, moles at equilibrium. Then these square brackets, remember, they refer to our concentration. So this is our concentration at equilibrium, right? Okay, so now we're going to fill out the numbers according to this, okay? So if we are to look at this now, what we are having is the initial number, right? Okay, so here what we're having here is 2NO2. If I'm to write again the equation according to this, we're having 2NO2 to give us that. Okay, so let me just like rewrite the equation here. So originally we're having 2NO2, which is a gas. Take note, this is a gas, and then to give us a reversible reaction of N2 O4, which is also a gas like that. Okay, so this is our original equation that we're actually having. Therefore, here I'm to actually start. I'm going to start by filling out the numbers there. Okay, so the ratio here, what's the ratio between this and this, right? So you can see here, according to this, the ratio is going to be 2 is to 1 like that. So we're having 2 of NO2, and then here is more of like we're having an invisible 1 like that, right? So the ratio here is going to say 2 is to 1. That's our ratio there. The R represents our ratio, right? So initial number of moles, right? So here, according to this question, this is what we're looking for because it says calculate the initial number of moles of what? NO2. So this is our unknown here, or our X, the one that we're looking for, right? So initially, remember, you start with the reactants to formulate your products, right? So if you are to start with your reactants to formulate your product, it means initially we are having a zero of the products, right? So graphically, if I'm to show this one, right? So we're saying here our reactants are getting used up to formulate our products, right? So you can see if we were to write it in terms of a graph, it means our reactants, they at the start, they will start with what? With 0. So these are our products that are going to start at 0, then they start what? Formulating like that. So our reactants here, our products here are going to start at what? At 0. So initial moles of what? Of our product is going to be 0. Again, here we're given the values for equilibrium. They're saying at equilibrium, the constant for the reaction is 171 at 25 degrees, right? So now if I'm to write my Kc expression, right? So remember, Kc is equivalent to the concentration of my products over the concentration of my reactants. Therefore, my products are these ones, right? So my products there is N2O4, O4, all over the concentration of my reactants, which is NO2 square bracket NO2, right? Okay, so since there are two moles there, we say 2, right? Okay, so if I to go back at the data there, again, we're given the equilibrium constant, which is your Kc, is given as 171, right? So we're having our 171 as our Kc. Therefore, I'm going to say 171 is equivalent to the concentration of N2O4, which we currently do not have in this case, right? So it means here I'm going to say N2NO4. I'm going to return it as it is, concentration of N2O4, then all over the concentration of NO2, right? So if I'm to go up a bit there, you can see that it reads here at equilibrium, the concentration of the NO2 gas is 0.2 moles per dm cubed. So it means we're having this concentration, right? So here we're going to say our concentration is 0.2, right? 0.2. Okay, take note now. When I'm writing here the concentration, I'm no longer using square brackets because we don't have a concentration of a what? Of a number. Then we square that one. Then after this, we are supposed to make the concentration of N2O4 the subject of the formula. So this is same as 171 multiplied by 0, 0.2 squared, right? So if to do my math right there, I'm going to get a value of 6,84. 6,84. Okay, so this is concentration. I'm going to say mole per dm cubed. Okay, so this is what I'm having here. This is what I'm actually having here. So after that, now I now have the concentration of this one, which is 6,84, right? So if I'm to go up there on my concentration of N2O4, NO2, 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 okay? So N2O4 is going to be a value of what? So this is my concentration at equilibrium for N2O4. So I'm going to just like substitute it there because it says concentration at equilibrium. So I'm going to write that value 6.84 like that, right? So I can just say mole per dm cubed, right? Then here we already know for NO2, which is our reactants there, we're actually given already, which is what we're given as 0.2. So I'm going to write that one down as 0.2 mole per dm cubed. Okay, so another trick here is that we're going to like add values and all, right? So what I'm going to do here is that I'm going to say put a negative here in change of modes, right? So I'm going to put a negative here. Why do I use a negative here? Is because here there is a change in modes. These are actually getting used up. While on this other end for the products, I'm going to put a positive. Why a positive? Is because here we are formulating. So we are adding something in terms of what of the products. We are formulating more products, right? Then after that, now we're going to look at the equilibrium moles. So it means moles at equilibrium. How many moles do we have at equilibrium, right? Okay, so if we're going to go up there at the top to look at the volume that we're actually given. So it says here, when the equilibrium is reached, the volume occupied by the reaction mixture in the gas range is 80 cubic centimeters. So we're given a volume of 80 cubic centimeters, okay? So now let's go down there and then just like to put a demarcation there, then go back to my color blue there. Okay, so I'm going to like look at the concentration of our NO2, right? I'm going to say C concentration of, let me just like say NO2 so that is specific, is equivalent to, how do we calculate concentration? According to our data sheet says concentration is equivalent to number of moles over a volume. So now, do I have the concentration of NO2? Yes, we already have. We're actually given the concentration of NO2, which is 0.2. So I'm going to say the concentration here is going to be 0.2 is equivalent to N, right? Remember, what we are trying to get there are the number of moles, equilibrium moles, right? So it's N over the volume, right? So the volume there, take note, is also given as 80 cubic centimeters, right? So it's 80 cubic centimeters. Therefore, we are supposed to convert this one to dm cubed. How do we do that? We divide by 1,000. So if we divide 80 divided by 1,000, what we actually get, we're going to get a value of 0.08 dm cubed like that. Okay, so it means this is our volume at dm cubed. Always take note, your volume, you should actually use a dm cubed. So if you're given in cubic centimeters, you divide it by 1,000 to get your dm cubed. So here, that's the value that I'm actually having. So I'm going to say 0.0 there. Therefore, I'm going to cross multiply to make n the subtract of the formula. So your n there is going to be equivalent to 0.016 moles, like that. These are the number of moles that we're having at equilibrium for NO2. So I'm going to just like substitute the number of moles that I'm actually having for NO2 there, which is 0.016 moles, like that. Okay. Then after that, now I'm also going to do the same for N2O4. Calculate the number of moles there. Okay. So let's work out the number of moles for this one. Yeah, I'm going to do the same again. So concentration there of N2O4 is equivalent to the number of moles all over a volume, like that. Okay. Do we have the concentration of N2O4? Yes, we calculated it to be a value of 6,84 there. I'm going to say 6,84, 6,84 is equivalent to number of moles all over the volume. So the volume there is going to be the same, which is 0,08, like that. Okay. So now if I'm to do my math there, I'm going to say the number of moles is equivalent to, if you cross multiply 0,08 multiplied by 6,84, you're going to get a value of 0,05472. Okay, so if you are to round off this one, you're going to get a value of 0,55, like that. Okay, so I can just say a value of what? 0,55 moles there. Okay, so now let's look at this. Our table. If we are to look at our table there, so initial number of moles, we're saying we're having 0. Then after formulating something, after adding something there, we end up with how many moles? 0,55. So it means how many moles were added here from 0 to 0,455. So it means we added how many moles? 0,55 moles, right? So we're having 0,55 moles. Then on this other end here, how many did you actually have? Right? So for you to get to this one, now we are going to use the mole ratio, right? Okay. So the change in moles here, you are going to use the mole ratio, right? So if you look at this here, we're having 0,55 on this other end, right? So according to this mole ratio here, let me use black. So according to this mole ratio here is 2 is to 1. The ratio says 2 is to 1, right? So now what we're having there are the change in moles, right? So if we're having the mole ratios that says 2 is to 1 like this, right? So I'm going to just say here, let me just like go down a little bit. So if we can just like, okay, let me use the top part there, okay? So if we're having here, the mole ratio is 2 is to 1, right? So what we are saying here, if we're having 0.55 moles on this other end, how many moles are we actually going to have on this other end, which is 2 of NO2, right? So take note, the ratio is 2 is to 1. So it means if we're having 0.55 on this other end, it means here we're going to have double the number of what? Of moles, right? So if we're to have double the number of moles, it means now our value is going to be if we are to double the number of moles, so now what we are saying here is 0.55 multiplied by 2. I'm going to get a value of 1, 1, right? Like that. So now the change in moles is going to be 1,1 moles, like that. Okay. So now let's look at this now. So how do you now go about to get the value for the change in initial number of what? Of moles. Now, how do I get to get the value of the initial number of moles? So what I'm going to do here is that I'm going to say mathematically, let's say we're having an A here, then a B here, and then a C there, right? So this is what we're having there. So allow me to use the top part there. So we're saying initial moles, right? So what we started with minus this one, we're going to get the final, right? So it means here, mathematically, I can say A there representing my initial number of moles, then I'm supposed to subtract here. Remember, I said minus in terms of the change in moles, right? So minus B is equivalent to, I'm going to say, is equivalent to C, which is my equilibrium moles, right? So in this case here, it means I'm looking for A. So in order for me to make A the subject of the formula, therefore I'm going to say my A is equivalent to C. If I'm to transpose my B there, I'm supposed to what? To add there. C plus B. So after that now, I'm going to say my A there is equivalent to, therefore my A there is equivalent to, and I'm going to substitute with the values from the table, right? So according to this, my C there, my C represents what? 0,016 moles. So I'm going to say 0,016. Then I'm supposed to add my B plus B. If you look at B there, we had a value of what? 1,1, right? So if we were to add these two, we're supposed to get a value of what? Let me just like quickly add this one. So it's going to be 1,1, 1,1, not 11, 1.1 plus 0,0,01, delete 0,016. Okay, so it's a value of 1,1,116, right? So it means our final answer there is going to be 1,116 moles there. So those are the initial number of moles of 2NO2. Okay, hopefully you actually understood and enjoyed the video. Thank you for watching.